welcome to the so called last lecture or concluding lectures of this course, network analysis, lecture number 82nd. And last time what we were doing, we were telling you about several problems where op amps are used as inverter, inverting amplifier, and inverting amplifier means there must be a negative feedback. While writing down the problems, perhaps in the first place I wrote it opposite. There must be a negative feedback. So, this sign corrections, please note that. Calculation part remains same. Okay. So, these rules, that is the voltage of this point and this point are same, is true if there is a negative feedback with a passive element like some resistors, inductors, capacitors, whatever it is, and there must be negative feedback. And today I will first tell you about one interesting circuits based on op amp, which will transform some general impedance transformation it will be able to do. For example, in a transformer we have seen, if you connect an impedance Z2, it will in the from the input side it will appear to be a square into Z2, where A is the number of turns. Similarly, we have seen if in a two port network when it was a gyrator, the input impedance is proportional to 1 over Z2. Okay. Now, here is a circuit which with which you will be a general impedance transfer circuits. Let us first draw the circuit without much words, so that you will be able to understand what I am doing. For example, you take 4 impedances. Although I am drawing resistances, it is true for any impedance, say Z1 here. This is another impedance. I could also draw a box, but anyway Z2. Suppose there are 4 impedances you connect, Z3, and you have Z4, very interesting circuit, Z4. And this I will use as my input, or here this is my output. Now, what we do is that we require 2 op amps, and these op amps are connected in this way. Three terminals, input output, and this one, this is plus, this is minus, and these 2 points are connected here. This I will connect a little later. Identically, you have another op amp which is connected here like this, and whose inputs signals are connected here, and the other one is here. This is how it is connected. Now, what is done, this third terminal, that is the output terminal, it is connected there, and this one is connected here. That is all. And of course, I must mention the polarity of this one. See, look at this op amp. Here is some output voltage of the op amp with some negative feedback ultimately attached to it. Similarly, for this. Now, this is the thing. Okay, suppose this voltage is V1. First thing is this connection is complete? Yeah. So, this is the V1. See, looking at the networks, we know these op amps, you treat them to be ideal, therefore, there cannot be any current here in the input side of the op amp. So, what will be the voltage difference between these two potentials must be same. Therefore, it is V1, it is V1. Therefore, the other one has to be V1. So that the voltage difference between them is 0. Got the point? So, the voltage, so if it is V1, I can immediately say this point cannot but be V1. That is all. Similarly, if it is V1, voltage difference between them is 0. Applying KVL simply. This potential I know with respect to common ground potential, all the potential. This potential I know. Therefore, here the potential difference is 0. So, there it will be V2, which is equal to also V1, has to be. So, this is the first thing, just looking at the circuit, I find this has to be true. Now, what we would like to do is this, we would like to find out the impedance seen by this circuit, and what we will be doing here is that we will connect another impedance here, say Z5, which is grounded. Okay. So, all the potentials are with respect to this as V1, I1. Now, let us see the currents. This is current I1. This ideal op amp, it will not draw any current. Therefore, this I1 has to flow through this Z1 as well. It has to. This I1 comes over here, but this current I cannot comment. It will not be same as I1 here. That will be different. Suppose I say that this current is I2, then there is no current in this branch. Therefore, applying KCL here, it will also give me this current to be I2. It has to be ideal op amp. Therefore, this is I2, this is I2, this is I1, this is I1. That is good. Now, we would like to find out this voltage. Mind you, this V2 is equal to V1. I concluded, and also this point potential is V1. That is what I concluded. Now, what I will assume is this current, let us say this current is Ix. If this is Ix, this Ix comes at this point, but this op amp does not take any current. Similarly, this op amp. Therefore, same Ix will flow here as well, is not? I mean, 4 lines derivation simply. So, given this network using 2 op amps, we come to these conclusions, and we would like to find out what is V1 by I1. Is how much, that is impedance seen from the input side is voltage applied divided by the current. Achha, now look at Z1 and Z2. Z1 and Z2, if you look carefully, they are in parallel. Why? Because there is a common point. This end are connected here. What about the other ends of Z2? There is no voltage difference. So, the potential of this point is same as this point. Therefore, Z1, Z2 are in parallel. It has to be. If that be the case, then I1 into Z1, voltage drop across Z1 with this is plus, this is minus, is I1x. And about this one, what is this voltage must be equal to Ix into Z2. But you see, if you write like this, this is plus, this is minus, this voltage is Ix into Z2. But potential of this point I have to find out, potential of this point with respect to this is equal to minus x into Z2. So, this is one equation. or alternatively you can say this is minus I x is flowing. So, this is plus are joined. So, in any case I 1 z 1 equal to I x into z 2. This is one equation. Similarly, we conclude that z 3 and z 4 also in parallel. Why they are parallel? Because this is the common point of z 3 and z 4, this is the common point, one point, and the other point of z 3 and this point of z 4, voltage difference between them is 0, because no voltage between these two. Therefore, they may be considered to be in parallel, and we will then have potential difference between these 2 points is I 2 into z 4, I 2 into, that is this side plus, this side minus, will be this one, and potential difference between these two is this is plus, this is minus I x into z 3, voltage difference. Is not that? So, therefore, this I 2 into z 4, this voltage plus, and here it is minus. So, it will be once again that negative minus I x into z 3. This will be the thing. Acha, if this is the case, then I can divide these two equations and get this relationship I 1 z 1 divided by I 2 into z 4, I x goes away and you are left with z 2 by z 3, like this. Therefore, this is the thing. So, this is one equation. Now, you see, look at this loop V 2, which happens to be equal to V 1, will be equal to I 2 into z 5, or V 1 is equal to z 5 into I 2, and this I 2 I will express in terms of I 1, which will be z 1 z 3 divided by z 2 z 4 into I 1. Therefore, I can write that V 1 is equal to z 5 into I 2 was there, and for I 2 I substitute this thing, that is z 1 z 3 divided by z 2 z 4 into I 1, or impedance seen from the input side, impedance seen from the input side is V 1 by I 1, Z in, let me call it, and that value is equal to Z 1 Z 3 Z 5 divided by Z 2 into Z 4 into that is all. This is the thing. Now, what you do is this that you suppose we say that let Z 1 equal to Z 3, you set these values Z 1 Z 3 is equal to Z 5, suppose some R, some resistance I will connect, and also equal to Z 2. Suppose all are met resistance, They may be different values also, but resistance I make. And then suppose Z4 is this one. Although resistance symbol I have drawn, it can be drawn by a box, but it could be any impedance Z4. So, Z4 what I do, I make it capacitive, that is 1 by SC. Before that, let me see. Therefore, we say Z in is equal to under this condition, it will be R cube Z1, Z3, Z5 divided by R and 1 over Z4. And I can say that this is R square by Z4. Therefore, the input impedance seen is the reciprocal of Z4. Now, if Z4 is capacitive, suppose 1 by SC, or say inductive, or say capacitive Z4 equal to 1 by SC, then I will say Z in equal to R square by Z4, which will be equal to R square C into S. Now, so the impedance seen from the supply is S into something, is not it is equal to some S into L equivalent, because for inductance only the impedance seen is SL, for capacitance 1 over omega C. Similarly, if you think Z4 is an inductor, so this reciprocal business will make it either, if it is inductor, it will be capacitance and so on. In general, if Z4 is any form, say Z4 is equal to 1 R bar plus J x bar, then 1 over Z4 will be ultimately some R equivalent minus J x equivalent. Therefore, this sort of circuit can be used. What happens is this in very large scale integrating circuit, if you want to simulate an inductor, between these two terminals you would like to connect an inductor. Inductor, you know, requires a magnetic circuit with lot of turns, size becomes more bulky. Therefore, instead of that you can connect, if you connect an inductor here, it will appear to be a capacitance between these 2 points. Therefore, you can replace this inductor by a capacitor, is not? Or if you connect a capacitor instead of inductor at Z4 connect a capacitance, then this points, input points V1 I1, it will treat this to be an inductor. Nothing is better than that. That is, you are using a capacitor can be made tiny compared to an inductor, and it can be accommodated in your circuits. Mind you, these are not power circuit, 220 volt circuit, 230 volt circuit, not like that. Control level voltage circuit, where if you want to have different impedance seen by this side, you can make it. There are various versions of this, it may be floating inductor, this, that. I will not go into those things, but only as an application of an ideal op amp circuit. I think it is very interesting, and initial circuits proposed by some name by somebody whose name I have forgotten. You go through the textbooks, you will find that there was a paper on that. Therefore, this circuit therefore can be treated where Z4 is the thing. Here I will connect the things and this impedance will appear different looking from this end. Anyway, this you do, and not but the least, last time I told you I will tell the name of the books from which I solve this problem. Please see, for problem solving this book. There are many in general for all circuit topics that I have covered. There are many worked out examples, also examples to be done by the students are given in this book, whose name is this book is. You go through the worked out example as well as your own examples, including the op amp circuits here. It is like fundamentals of electric circuits. Electric circuits by C.K. Alexander, and M.N.O. Sadiko. Very good book, Sadiko, for problem solving, and this one also ideas, you can get newer ideas. It is by Tata McGraw-Hill publications, Tata McGraw-Hill publication. You can refer to this book. Achha. Now, today what I will be doing, this being the last lecture, I will try to summarize the whole course. Okay. And before that, while going back myself, I found only one theory I forgot to mention. That briefly I will tell, very simple theory, and that is called Millman's theorem. Millman's theorem. Very simple theorem, but useful. What it states that, suppose if you have a network having Z1, there is some voltage source V1, they may be phasors, impedances, DC, AC, whatever it is. There are other source Z2 and here is V2. There are several sources like this, Z3, V3, like this. There are several voltage sources with impedances, and here maybe you have connected a load impedance Z. Then how to find out the currents flowing through all the branches as well as this impedance in the output circuit. So, this current may be I1. So, you see this is the current I. Now, what I will do is this, what is the best method of solving this? There are only two nodes. Okay. So, consider this to be reference node and consider this potential is V. If you know this potential V, then you can find out any branch currents you like. That is the idea. So, write KCL at this point. KCL gives what? The current in this branch I1 will be V1 V minus V1, this way I have directed. So, V minus V1 by Z1 plus V minus V2 by Z2 plus V minus V3 by Z3. all current going out, this current I 2 is this one, this is I 3 and this is plus I, which is equal to plus V by Z, and that must be equal to 0. Therefore, you can see that V is the unknown 1 over Z 1 plus 1 over Z 2 plus 1 over Z 3. I could write it in one stroke also. We know the rules, all impedances connected, sum of the reciprocal of the impedances of this node, only this node voltage is necessary, and so this is the thing, and this will be equal to V 1 by Z 1, take these terms on the right hand side, and V 2 by Z 2 plus V 3 by Z 3. Therefore, this voltage V is equal to V 1 by Z 1 plus V 2 by Z 2 plus V 3 by Z 3 divided by sum of all the impedances, reciprocal. So, in Millman's theorem, it says that if this kind of circuits are there, several voltage sources along with their internal impedances connected in parallel, and it is supplying a load, then this voltage can be easily found out. So, what it will be V 1 by Z 1 plus V 2 by Z 2 plus V 3 by Z 3 will be this, and this will be equal to 1 by Z 1 plus 1 by Z 2. So, this is the formula used here. So, this is Millman's theorem and can be applied in circuits wherever you place this. So, after you get V, then I 1 you have to calculate, this is I 1, calculate I 1, calculate I 2 and calculate I 3 in the usual way. Okay. So, this theorem was somehow I forgot to mention. So, today I mentioned it is 2 lines derivations. After you have gone through this course, this is nothing. I mean, you can just assimilate this. Now, now coming to the concluding part of this whole course. See, in this course, we have started from the very basics about, so concluding remarks about the course, concluding remarks. First thing is, we started from the basic KVL, KCL equations, then mesh analysis, the usual stuff, analysis, then nodal analysis, is not these things we did. And then first I introduced this with DC sources, but later it was modified to AC sources as well, if you are interested in steady state analysis, or even if you are interested to find out the solution along with transient part, then Laplace domain is the best one. But before that, to solve network problems in time domain, we require to solve differential equations. Okay, and before that I introduced with sources, that is voltage source and current source. And in the latter half of this course, we also talked about dependent, these are called independent sources, dependent voltage and current sources may also be present, dependent voltage and current sources. This we discussed somewhat at the latter end of this course. But anyway, this was sources. Then we know how to write down KVL, KCL in time domain. So, solution of differential equation. I spent quite some time solution of differential equation. That will be necessary if you want to find out the total solution for currents in a circuit which is excited by time varying sources. So, solution of differential equation, and that is the classical way of solving a circuit equation, classical way. Okay. After you have done this, so it also gives you both time domain as well as steady state response. See, the usual order of any circuit, time constant of the order of some milliseconds, or in terms of supply 20 millisecond period 50 hertz supply, there may be 2-3 cycles of supply. So, after that only steady state prevails. Then we introduce the phasor notations, how to get the steady state solution straight away. That is also an important thing to know. Okay. So, solution of differential equation. Later we found that the solution of differential equations can be replaced by a Laplace transform technique, Laplace transform. To solve network problem, So, some basics of Laplace transform I told, then several circuits can be solved. Only thing, wherever there is inductor you replace it by SL, wherever there is capacitance you replace it by RC, and R do not do anything, R keep it there, and supply voltage Vt change it to Vs. Any currents in the circuit It change it to Is. Then what happens is this Vs becomes equal to Zs into Is. Therefore, I can invoke all the rules that we have learned in DC circuit, because it is also linear so far as Zi is concerned, Z is a constant thing. Therefore, for any input voltage I could find out the value of Is as Vs by Zs. It is a very popular technique, and take the inverse to get the current domain solution. Replace S by j omega, you will get the solution when the supply frequency is AC, otherwise it covers all the types of signals. Remember, I also discussed somewhat at length that what happens if the source is somewhat awkward source like impulse source response of a circuit. Response of a circuit means maybe current response due to an impulse. Now, of course, all these rules were developed for linear time invariant circuits, and therefore, several interesting rules were developed. Then the network theorems, these are very important things. Network theorems, what I did was several network theorems, whatever I could recollect, I will tell that. Network theorems, various network theorems, of which one of the popular theorem is substitution theorem. That is, in any circuit, in any branch where there is an impedance, but if it is carrying an current I, you can replace that branch by a current source I, things like that. We know that. Then we did the most important theorem, Thevenin's and Norton's theorem. their applications, how to find out those equivalent circuits when the sources are independent sources or also when there is a mix up of sources, both independent and dependent sources are present. So, those topics please go through them, they are very interesting, and this one. Then we did theory of reciprocity, these things, theory of reciprocity. Okay. And then today, for example, we have done Millman's theorem, which I missed earlier, Millman's theorem, things like that. Then the major topic I covered in this course is what is called the network analysis with graph theory, network analysis with graph theory, considerable lectures I have taken. And I have only, because graph theory itself is a very big subject, I have only applied the graph theory, which is absolutely essential and a very easy way you can go. And graph theory generally is applied to solve a circuit if the network is big, and then you write some codes in a systematic way, you can find out the currents or voltage. Here also several theorems like cut-set matrix, this that we have considered. So, go through that part also. Then network analysis, after that we have done two-port network, two-port network. And here also several lectures I have taken to find out several representation of two-port network, what a two-port network is, and impedances, impedance representation, Z matrix, then T matrix, which is nothing but ABCD matrix, then H matrix representation, and the inversion of Z is Y matrix, ABCD inversion, no name is given, I think something, H parameters, its inversion matrix is G matrix, conductance matrix, and so on. And when the networks are connected in cascade, it is better you represent in ABCD parameters, so that the overall ABCD parameters of cascaded networks will be simply the product of T matrices. Then we consider two important elements, one is called ideal transformer and gyrator as a two-port network, And finally, we did some circuit using ideal op-amp, with negative feedback, that is important, feedback. And the analysis of this type of circuit is very easy, and after you have gone through these courses, I hope you will be able to do that. So that is all. I do not know, there might have been mistakes when I have written so many things, which I might have overlooked. My sincere request to you will be, if any such basic mistake comes to your while you are going through this lecture, if you find, oh, there is a mistake here, please point it out. I will try to correct in the later stage. Wish you all the very best for this course. It is a nice course. Last thing about this is I find that network analysis is a beautiful course. It will challenge your intellect. See, it is solving a network problem is an art, and I may not be the best artist. I do not claim that. Maybe one of you are one of the best artists, because I have handled several students. Students will come up with solutions I find amazingly beautiful. Okay, I was thinking this way, this problem could be solved that way. Very nice course. So, I have tried to give you ideas how to really handle networks, which may be complicated, which may be tricky, whatever may be, but you have your own approach. Do not try to remember so many formulas, stick on the basics. And always remember, in any network problems, the concept of energy balance is another interesting thing where things can be done. Okay. So, with that, with best wishes to you all, I close this course on network analysis. Thank you.